Hello and welcome to today's presentation on cover meter operation and the Profimeter PM8000. I'm really glad to be here today. Let me begin with a quick screen share and we'll just cover what's new from PCTE and from the Screening Eagle technology range since we last spoke. Something which is always worth keeping in mind is we are getting better and better ways to bring the data from the Screening Eagle technology hardware across into data handling tools. That might be Screening Eagle Workspace, which is their cloud service for data export and record keeping and transfer from your live service devices. But it's also things like Screening Eagle Inspect software. Also today, I'm pleased to be introducing the latest generation of the Profimeter cover meter. That's the PM8000. We can see the original Profimeter here. And now we have what we're showing today, what we've come to. And we'll have a full demonstration of the application and the cover meter operation as during today's presentation. We'll get towards that towards the end. So once again, we're going to begin. Now, does that video come through clearly for everyone? Is everything flowing smoothly on the operational side?
Yeah, looking good.
Now we're good, yeah.
Excellent. Thanks so much. So look, what I'm going to do from an education standpoint today, I want people to understand the pulsed eddy current cover meter theory. I always like to talk about this for cover meters because what makes them such a precise measurement tool, but it's also something where it's easy to get it wrong or to not see how it makes the procedure need to be a careful one when using the tool. We'll also talk a bit about what we can measure and what we can't measure of different reinforcing types and structures and ways of building things. We'll look at how to scope up a cover measurement procedure. So I've got everything from basic spot measurements, which might be great for quality control, up to a overlaid 2D map of the reinforcing layout, which is ideal for showing an output to someone for here's what you really have, and here's the bits that are of concern. So we'll go through all of that. I'll give you a procedure, which I personally like as a way to get a precise, careful cover measurement as unaffected from interference as possible. And I'll show a bit of data handling and interfacing between things, just so we can see that as an operator, you don't need to be tied into lots of hand notes, laborious re-entry of data. You can have it flow through to the final output. So just to begin, the specific context today is eddy current cover meters. Specifically, the Profimeter PM8000 is my example tool, but my general scope is any eddy current cover meter. That contrasts to something like a ferromagnetic cover meter. Basic principle between those two is a ferromagnetic cover meter is detecting ferrous metals like iron and steel, whereas an eddy current cover meter is detecting conductive metals. It's only precise for depth measurement on your conventional steel reinforcing, but it can be affected by and interfered with from other metals, including non-ferrous metals. Other tools we've seen in the context which are similar are tools like ground penetrating radar, which is more about an overall scan of a structure. Yes, it will find rebar and the depth of that rebar, but not as precisely, but it can do multiple layers. It can do the overall thickness and other embedded objects or other forms of reinforcing like post-tensioning, carbon fiber or glass fiber reinforcing steel, more esoteric scanning requirements. Now, ultrasonic I always like to mention in the same breath as GPR because it's got the ultimate sensitivity. It's not as good for finding rebar, though there's a few jobs where maybe it's the only tool that can find rebar, but it's also capable to find voids and defects much more effectively. And if you've attended any of my previous presentations, you would have seen that there's a lot we can do for void, defect, and damage detection using ultrasound. So our scope today, specifically eddy current cover meters, for precise cover depth measurement. So to find cover depth, the depth from the top surface of the concrete element through to the top of the reinforcing steel, the amount of concrete that sits between the outside world and the first piece of rebar. Why is this measurement so important? And it comes back to the long-term durability of a structure. We are not living in a kind-friendly world. There are always sources of corrosion out there, things that want to break down our materials and entropy to bring down our built structures. Now, for reinforced concrete, they are great partners, the concrete providing building materials, the steel shoring up its weaknesses in tensile force and areas like that. And surprisingly interesting how they mate together and have similar expansive quotients. But steel's biggest enemy is corrosion. And it's the elements in the environment that affect it. If we get salts, so what I call here chlorides, or we allow the carbon dioxide in the air to diffuse to the concrete to the level of the reinforcing steel, that's what begins to cause a big breakdown of a lot of our structures, which is reinforcing steel corrosion. Cover is the first and best protection against this corrosion. And you can see that in this example here. I've got a couple of little charts. A chart's not quite as bad as an equation for a slide. It only means one person leaves. But we can see that with carbonation-induced corrosion, that's carbon dioxide diffusing from the air, might be heightened in something like a road tunnel. If we remove 2 millimeters of cover, so our design cover was 20 mil, and the actual cover was 18 mil, it can have a 10-year reduction in the expected life of that structure versus the design life for cover not to be achieved during construction. Similarly with chloride-induced corrosion, going from a 55 mil cover to a 50 mil cover in this example, we see a 25% reduction from 50 to 40 years expected life of a structure. And this sort of information only becomes more important as we start looking at 100-year design lives. We need to prevent the outside world getting to our steel for the long-term health of our structures. So this is not a corrosion presentation. There's always the chance to go back into more detail on these areas. But I do want to highlight this as we keep going forward. So I did ask you all to send me a few questions before we begin today's presentation. There was only a few that came in. Someone wanted to see a comparison of the PM8000 to the Profoscope Plus and Profimeter models that were available from Prosec or Screen Eagle Technologies before. The basic thing there is the PM8000 is available in two models, a PM8000 Basic, which is only a spot measurement cover meter, and that's loosely feature equivalent to a Profoscope Plus cover meter, which is one of our most popular products prior to the launch of the PM8000. Whereas the PM8000 Pro, which has full integration with the PM Cover Meter app, goes to the same level and beyond the functionality of a Profimeter PM650. So the PM650 offered cross-line scan, showing the reinforcing steel in two directions on a structure. It also had the ability to import and export full presentation, do another variety of tools. The only functional difference on the Profimeter PM8000 is that the app goes a step beyond. It includes augmented reality, a cloud-based data flow, but currently it does not integrate a Profimeter corrosion capacity. So your half cell potential measurements would still be done using a different machine. If this is a cover meter only at the current set of configuration. Now, best results for reinforcing size and position, I will be covering during the general presentation, so please hold on, along with the depth and accuracy of the PM8000 cover meter. Now, for depth of hold down bolts, generally, you don't want to be offset. Your successive location and measurement with a cover meter is very dependent on the reinforcing steel being oriented straight behind our scanning probe. And I'll show you how to do that as we work. But if you are on if you do have a more unusual job, things like maybe tie rods in brickwork, things like that, we can perhaps use our cover meter's signal strength detection as a tool. But I generally don't suggest using cover meters outside their their specific purpose, which is accurate, precise depth of reinforcing steel. That said, we do have other technologies we can bring in to our hunt for detail. So I'll be mentioning today Screen Eagle Inspect as a hub for data from all of these kind of machines and going beyond that. I'll also have, I've also already contrasted us performance to ground penetrating radar tools and ultrasonic tools like the Pundit Impact or Pundit PE and UPV. Schmidtham is a little outside the context of today, but our main focus is Profimeter, cover and diameter of rebar diameter, rebar characterization. That's what we're focusing on today. Now, back to our survey, and this is always something which I have to talk about every time because I've been working to support our customers in the industry with tools that are complex non-destructive test equipment. And I always see that people can be fantastic, skilled user of a complex survey process, but they maybe don't gain the same comfort and grasp with the data logging functionality of their tools. And I can see this again today. We had 94 people sign up for this webinar, and they each gave me a few notes about, how do you collect the information from your cover meter? Clear winner, and I did expect this, was they keep paper notes. They write down the cover measurements straight on a piece of paper with all the other notes from site. One of my absolute sort of least favorite ones is photographing the device screen, because then you compound the problem you have coming back from site with thousands and thousands of photos. Now you've got additional photos with no identity with the measurements on that cover meter. But, more than 10% of people are using internal data logging or the phone or tablet app. So let's call that clear. 20-30% of people do use the internal data logging function. So that's great. It certainly wasn't like this 5 years ago. And one thing I will highlight is that third-party data recording or database app. That's always an interesting concept. That's what Inspect is. So I'll show you that a little later. But in essence, by a database app, I mean a way to tie some of our cover meter measurements into a record of where we were and what we were surveying. So this is where I took my sample data from. It's just my office wall again. This is the most well understood office wall in the entire building, but I can store in my cover meter measurements in the same area. I think I had about a 55 there. So that's what I'm talking about when I talk about database apps. And the reason that I like these tools is, with paper, you can write things down wrong. You can't read your handwriting. If you're doing, you can do export from machines to CSVs or individual applications. That's fine, but you've still got to pull all those files together with the photos from site. It's nice to have cloud services so your data is not lost if your physical device or storage hardware is damaged. So this is not an Inspect presentation, but I always like to talk about the power we have available. I see Andrew's actually provided some context that not every paper note is equal. He's actually doing a survey with physical markup of the structure, chalk or crayon, and photographing the outcomes and using a dictaphone. So there's always clever ways to work. But sometimes we do have these tools that can improve our workflow for the same outcome and just allow us to prepare and document on site. All right, let's go into the theory now. I'm going to talk about the physics behind what we're doing and the accuracy and the limitations of eddy current cover meters. So this is a very simplified explanation of what we do with eddy current cover meter. We apply an alternating current signal to an electromagnetic coil. It induces a matching current in the reinforcing steel. We measure the strength of it. The cover meter becomes essentially a signal strength meter. And what that signal comes from is the presence of reinforcing steel close to our sensor. It's useful in some ways. We moved away from ferromagnetic cover meter measurements because there's less drift in this eddy current procedure. We've been using this in the previous generations, the Profoscopes and the Profometer cover meters, and in the Profometer PM8000. So if you're familiar with those previous cover meters, you're going to have the same capabilities and limitations on this. We haven't changed our measurement technique. We have changed and essentially combined the features of the Profoscope Plus and the Profometer PM range so that we have side to side and up and top and bottom coils to give the best location for our cover measurements. And I'll demonstrate that. So here's a better illustration of this eddy current measurement principle. The transmitting coil is energized with alternating current, produces an electromagnetic field. We get a corresponding current, so electrical energy induced into the reinforcing steel. It produces a matching electromagnetic field, and we measure with our receiving coil the strength of the electromagnetic field. Now, there's a couple of things we can do differently. We can put more or less current to the transmitting coil, which means the field it produces is bigger or smaller. And if we've got a bigger field, well, that means that it's going to fill a larger area. So if we're trying to move into very dense or complex reinforcing layouts, sometimes we want to limit the energy of our transmitted field. Now, there's two things we can change about the reinforcing steel that's near to our cover meter probe. I am assuming that the cover meter probe is correctly lined up over a single rebar. And our procedure I teach later is going to be all about correctly lining up your cover meter probe over top of a single reinforcing bar. If we have that reinforcing bar brought closer to our coil, the effect is going to be one of an increased signal strength. 1 second. The effect is going to be one of an increased signal strength. So, and it's going to be quite a substantial increase the closer that reinforcing steel gets to our cover meter probe. This is why we can call our depth measurements so precise. If we have a big change in the signal we measure, going closer or further away, it's easy to relate that to a change in the measurement we care about, which is distance cover meter probe to reinforcing steel. The other measurement that we can take with the cover meter is an estimation of the rebar diameter. And you're going to hear me harp on this again and again today. This measurement is an estimate of the rebar diameter. I consider and have seen with performance in the field that we don't want to use our diameter measurement as the first reference for bar diameters. It's a useful estimation tool, but if you're doing something critical like design work, you'll want to be using visual inspection as part of your process as well. But just to highlight, if I increase the size of the reinforcing steel, yes, I do have increased signal to my cover meter sensor, the eddy current procedure, but it's a small increase. And the fact it's a small increase means that it's much harder to establish difference of reinforcing bar size than it is to establish the difference of the depth of that bar. That's why I call it a cover meter measurement, cover depth measurement, and a rebar diameter estimation. Now, we do have some limits on these tools. Your maximum depth is controlled by how much energy we can kick out from those coils. And it's going to be somewhere from about 150 to 180 millimeters absolute cover depth. You will find that the deeper you go, the more difficult it can be to use the location function of your cover meter. So there's two things cover meters get used for where we roll them or move them across the surface. They can locate the reinforcing steel and they can measure the depth of it. The ability to distinctly see an individual bar is lost before the ability to measure its depth is lost. So we're never prevented from doing a useful cover survey, quality control, making sure we've got sufficient reinforcing cover. But if this was being depended upon as our reinforcing bar location tool, that will be unavailable if bars are too deep and too closely spaced together. The bar pitch is too small. We do have correction factors to account for any interference caused by the bar pitch being too closely located. So I'm going to talk about accuracy now. In general, for accuracy of the measurements, we've got a standard measurement range and a deep measurement range. And within the first 40 millimeters, we have a 1 millimeter precision on the depth measurement, provided the correct reinforcing diameter is entered. And I'll talk about reinforcing diameter entry as we talk about using the cover meter. The diameter measurement is only possible down to about a maximum of 50 millimeters. And that precision is a number I wouldn't give a plus or minus value to. But just to read off the rest of the chart, once we get close, so at 0 to 40 or 50 mils depth, we have a 1 millimeter precision for cover depth measurement. Around about the 80, 90 millimeter mark, we're creeping up to around a 3 millimeter precision and about 4 millimeter precision at the absolute maximum range of the cover meter, out to that 180 for quite large reinforcing steel. And there's about a 4 millimeter variability in that number. So the closer, the better. but we are achieving some of the requirements like the Vic Roads requirements for 1 mil at 40 mils depth precision and cover meter measurements. Now, we need to, when we're setting up our cover meters, enter in information like the expected reinforcing diameter. And people always ask the question, well, it wants to know the diameter. What do I do when I don't know it? First answer, work it out. Find a drawing, break in and inspect the reinforcing steel is always your best way. If you want a really precise and careful cover meter survey, it's always good to include 1-2 points of visual inspection to confirm the measurements of the machine and make adjustments if necessary. But if we don't have the ability to do that, we do have to start making assumptions. Now, first thing, default setting, what I set my cover meter to, if I don't know the expected reinforcing steel size, is 16 millimeters. And the chart I've got on the screen shows the different uncertainties those settings have. So if you've got a 60 mil depth bar, and that bar size, we don't know it, but we think it might be as small as 8 millimeters and as high as 20 millimeters. The uncertainties around a plus 50 millimeters, so it could be 50 millimeters deeper than we see on the scan, and a negative of 2 millimeters. So we could see it as closer to us than 2 millimeters. This might not be a good setting configuration because it's likely we're overestimating the cover depth in this case. And if we're using it for quality control, we don't want to overestimate. So maybe there'd be a case to change that setting to a smaller bar diameter and push our variability towards under-reporting cover rather than over-reporting cover. Okay. So now I know there's a question about precision and accuracy. Does that answer some of those questions, or would you like me to stop and talk a little more or provide a little more detail about that? Again, I also am watching the chat, so if you don't want to speak up, feel free to drop questions into the chat. All right, carrying on then. Thank you very much. Oh, so the chart, I can send that across as part of my wrap-up email. I'll include that when I finish the webinar today. Thanks, Luke. Now, the diameter estimates. The way the diameter measurements work is we have a standard and a deep measurement range. It's possible to compare the result from a standard and deep measurement range and to look up from a table of expected results what diameter would cause those two measurements. Again, the difference in signal is quite limited going small bar to large bar. So again, this is an estimation of this measurement. It's not something I want to give an assumption on. The other thing is this measurement is very heavily affected by other reinforcing steel. So if you don't have a single bar miles away from every other reinforcing steel bar and miles away from other metals, cables, second layers of reinforcing steel, there's lots of sources of interference that can make this look closer. One other source of interference that we do see is welded reinforcing. So if you have a welded reinforcing cage rather than a conventionally tied together set of rebar, the bars will look gigantic on the diameter estimate, and it will also provide more signal to the cover meter. So the apparent depth of bars that are welded will be more shallow, closer to the surface, than for unwelded reinforcing. So that's my basics. Let's talk about how we actually set up for a cover survey and what are our considerations during that process. So firstly, what is the scope of the job? I've got a couple here. Maybe we have an absolute minimum cover that we must achieve over the whole structure, and we're using our cover meter configured up to let us know if we're below that. So if you've got a 50 mil minimum cover, we can configure an alarm on the cover meter just to let us know when the cover is more shallow than that and scan the entire structure quickly. Spot checking. The only caveat I would make there is just make sure you're isolating individual bars. We'll talk about that procedure. It is possible to get false failures when you're doing minimum cover surveys. Others, we care more about the statistics. I've given a little image of the statistical data on the left there. Maybe we care about the average cover depth and are using that for calculations of durability or other factors. So we can get that straight from the spot measurement modes, line measurement modes, or the area scan measurement modes of the cover meter. Maybe it's about bar location or documenting the layout of the reinforcing bars. Again, we can use different survey modes to achieve that, and try and get away from only relying upon sketching on the surface the reinforcing layout. They don't discount the power of a sketch. I'll talk about that. Maybe we do need to use it for diameter estimates, but if we're doing that, not your master tool, physically inspect bars. Maybe the cover meter can help you know that that section over there is loosely similar to this section, but just don't depend on it. And maybe there's other specific jobs. Does anyone have any examples of jobs they've done with the cover meter or would like to do with the cover meter that are outside these examples?
Yeah, hi, William. Yeah, it's Ian Barnes here. We often use a combination of the Profimeter and the GPR, mainly to locate reinforcing and multiple layers of reinforcing, which
yes,
is
of
really
course.
the GPR, but primarily for coring holes in existing concrete structures to work out the safest place to do it, so you're not weakening the structure. Yep. And so, and yeah, what you were saying before about locating reinforcing, it's very difficult to keep a digital record of where the bars are, because you need some way of actually summarising that within the electronics of it. What we do is with the GPR especially, we have a file, we name the file based on where the scan was done. So when we look back at the results, and it's a manual way of doing it, but it does allow us to store data, store the images, and to present reports with those scans included. So primarily we're looking at the best place to core holes and estimation of strength of structures too.
No, Ian, I actually quite agree. It's very important when you are doing location work and you want that location result to be more than just marks on the surface, to record your information somehow. Yes. So now this project is a general project I did with a few different survey tools. I did use some GPR here. So we can see that when I documented a cover meter, a radar scan, I have information recorded of that, of photographic evidence, in addition to the position information stored. And that's how I would want to do that kind of work. I wouldn't want to just depend upon having memory. You need to have fixed points of reference on the structure where you know your scans start, where they begin with. You probably do need marks on the surface, and those could be photographed as well, but you also want to tie in the results of your survey into your record keeping through whatever means necessary. And it's just the same when we're doing digital. You don't just expect the machine to tell you what to do. You always have a planned out procedure of how you're going to locate on your plan the position of what you've worked on. So that's quite correct, Ian.
Okay.
Yeah, William, I'd love to be able to investigate steel sets behind concrete lining in tunnels.
Okay.
Is there, and usually the liner thickness is about 150 to 200, and you're dealing with a sort of, C channel. You reckon that would show up as some anomaly?
I wouldn't use a cover meter for it, because that before we even get to the steel set behind the tunnel liner, you've got 100, 150 millimeters of depth. We're going to a material that isn't reinforcing steel. We're doing C channel. So the cover meter's specific depth measurements are designed and built around conventional reinforcing steel. You would get a signal response. So if we look at...
yeah, well, that's my point, because I don't want to drag my nice GPR over the sewer surface.
Yeah,
so I just want to be able to run something in a plastic sheet across and go, yeah, this looks like.
So you do get a signal response on the chart. Now this is with the wheeled cart, but you don't need to use the wheeled cart. You can just move the cover meter probe in a bag over that. Your tunnel lining isn't steel fiber reinforced or anything, is it?
No, it's 16 to 20s at 200.
So
or nothing.
Okay, no problem. So basically, if we've got other reinforcing, that'll probably be the thing it finds with priority. But if you've just got that C channel behind there and it's big enough to kick a signal through the lining to our cover meter, the depths will be off with your initial calibration. In fact, the depths will probably be always a little bit different than the same amount of metal in a reinforcing steel bar. But there will be a signal available. And if you're doing some drilling or some other way to, or even mocking up that same kind of C channel, and you know the signal at a certain distance, you could set it up for maybe a go and no go by choosing a fixed reinforcing bar diameter and entering a minimum cover, which you can do in the control of the basic machine. And that works the same on a Profoscope cover meter. If you've got a previous generation unit, or the Profimeter PM models can do it too. So there's ways to go about it. It's definitely worth exploring the tool, but you'll need to document a sort of set of standard settings and what you consider compliant and non-compliant. It's not going to give you that number straight away. You're going to need to feed your number backwards into values from the machine that you're going to call good or bad.
Yep.
And you still got the same limitations. You need to be going to an isolated piece of metal, not other ones nearby. So watch out for that too. That might be worth workshopping a bit more, but it's a good example of another job. And this is exactly what this slide is basically meant to talk about: is what's the job, which machine can do it? Do we have to go to radar? Do we have to go, can we use a cover meter? Do we want the data logging diagrams, or is it just, can I find it and catch it while I'm working? And what kind of report are we kicking out at the end? And do we need a tool like Inspect to get to that report? So a few questions for you. Now, we've talked about cover meters. Some of you are familiar with radar and other survey tools. Let's start, let's do a bit of a pop quiz. If I have a minimum cover of 40 millimeters with a slab on ground, am I going to need something fancy? Can I just use a spot measurement? Do I use a cover meter? Do I use a radar? Do I use ultrasound? Do I get out the old dowsing rods and try that for location? What's my best tool and setup here? Don't all shout at once. Come on. I'm watching. So we've got a cover meter response on the chat. And yeah.
Depends what you're trying to measure.
Yeah,
What you're trying to measure, William. Are you measuring the thickness, GPR, or the reinforcement would be a cover meter?
That's right. And of course, if we did, I have given minimum cover for slab on ground, but you're quite right. You'd want GPR if you need depth of that slab on ground. So what about for a bridge girder? 100 millimeter bar spacing, additional reinforcing steel. So at the edges, so we've got a very dense reinforcing layout and the same minimum cover. Any thoughts about how this might affect our survey and our requirements?
I think you would need to be using GPR for that to get, so you can look through the multiple layers and get a sense of what you're actually seeing.
You know, you're quite right. For quality control, there are ways we can make use of cover meters as well. But if you came out on this job and you didn't have a drawing, or you only had a rough drawing, I agree. I'd pull a cover meter, I'd pull a GPR out. The cover depth wouldn't be quite as precise. I sort of consider GPR to be maybe within a centimeter of the real depth. That's my opinion. But it'll be the easiest task. One thing I will point out is you do have some cover offsets and some neighboring reinforcing settings, and especially some calibration modes on cover meter tools. So if it was a quality assurance job, if you're a precast yard that was making these girders, you could still use a cover meter procedure. Precast yards use lots of cover meter survey. They tend not to be GPR operators. They can be configured in a way to give them those critical measurements, or at least a go or no go. But if you're an inspector, yes, GPR every time, at least until you can find a spot clear to get a precise depth of the cover meter, an isolated bar. What about sort of similar question, an unknown residential floor, but it's a suspended slab. So we've got, again, cover meter is not a bad process, but it's a suspended slab. What do we have to watch with suspended slabs as operators of tools like this?
We need to have the reinforcing in the bottom of the slab at the extremes, in the top over the supports and the bottom at mid-span.
That's right. So that you might need to consider there could be two levels of reinforcing, or additional steel around details like columns and beams. Also, there's the chance it could be a post-tensioned construction. If it is post-tensioned, that can be more difficult. Now, I've got a couple of examples about scanning before drilling. I know that one of the attendees mentioned about drilling already. We've discussed that a bit, but anything else to think about where cover meters sit on this scan before drilling application?
So they may not pick up electrical cables.
Exactly right. And that's just one point of why a cover meter cannot be your master tool for drilling. Anything else?
Or plastic water pipes.
Yeah,
Or
look,
gas or whatever. Yep.
yeah, and we could list a dozen things. A cover meter is sensitive to primarily reinforcing steel. Now, this is an eddy. Now, the profimeter is an eddy current cover meter. So other metal, I call interference to it. So yes, it might get some effect from other metallic targets, but they could be too deep. We certainly can't find plastics. Frankly, scan before drilling is usually not a cover meter job. It's more of a ground penetrating radar job. There's a couple of very specific cases people do use cover meters. One of the more common ones is things like facade installation on piles, or basically something where the construction is already known. They already know it's only reinforcing steel, and they use the cover meter as a little handheld locator. That's okay. But if you don't understand everything there, you don't have you don't know how deep you need to go, I would steer well clear of cover meters for scan for location. What about some remediation considerations? What do we need to think about when using cover meters for dilapidation work or remediation assessments? Is there anything special there? I've got a few points I'd like to make, but I'd be interested to hear what the floor has to say.
I often use cover meters for dilapidation surveys over GPR just because of the fact we're looking for precise depth and the closest depth. Because as we saw in the first slide, it's the chloride carbonation is the biggest issues that we've got, and so you can do get lots of data and put in a big spreadsheet and do some statistics on things and map areas and calculate risks.
No, brilliant. That's basically one of the first points I wanted to make.
And also, the other thing I would probably add to that is when you have an existing structure that is already showing signs of corrosion of the steel, as in spalling of the concrete, you can very quickly look at other areas of the structure and sort of give an indication as to the other areas where it's defective and therefore likely to be experiencing corrosion in the future. And therefore, is it worthwhile repairing one place and then 2 years or 5 years time, you're doing the same thing with the rest of the column, or do you replace the column or reinforce it otherwise?
Yep, perfect. Now we've spoken a lot about how we can use these tools and which one to pick. Just let's talk procedure. The most important point with a cover meter is avoiding interference. We want a single reinforcing bar aligned straight along the measurement path of our cover meter, protruding a bit above and below the cover meter. And we need to ensure that before we take our numerical measurements. So we need to work out which bar is closer to the surface. And I'm going to start doing that by marking the position of my reinforcing steel on my survey area. And then I can bring my cover meter through an area completely isolated from parallel bars. By parallel bars, I mean bars that I am rolling my probe in the same direction as, and I can start to collect good cover depth value. Then I can resurvey my previous points, moving in between that. I've got an area scan video where I do exactly this. I'll show you in the demonstration section. So this is basically the way to master a cover meter. If you just push them on the surface and take the number off, you could be easily aligned with a bad measurement point. If I was to take my cover meter and put it right here, I'm going to be recording a cover depth that is too low. Whereas if I'm aligned perpendicular to the bar, so directly over top of that bar and isolated from the one surrounding it, I'm getting correct cover depth values. That is always your main priority. Also, with the Profimeter PM8000, it brings a feature back from the previous Profimeter, which is a signal balance. So I'll also show how to do a signal balance when you're doing a single line scan. So it is possible to take your cover meter probe, use it to essentially move it up and down over a region and isolate the center and then start scanning along. So I show that in my line scan demonstration, how to use the balance function, the top and bottom signal, to then go straight over isolated bars. Now, a little bit of interference. We want, and I've highlighted it in green, a single bar inside the electromagnetic field of the cover meter. If the bars get too close, we need to use our neighboring rebar correction function. You can see this here. It is used to correctly measure depth when bars are closer than 140 millimeters. And it considers bars in both directions. It's quite sophisticated. I'm not going to teach this today because this is more about general processes. Other cover meters might use things like spot probes that have a more narrow electromagnetic field, but this is the Profimeter approach. The other one to highlight is we have our measurement ranges. So this is in standard, and I like to keep my cover meter in standard unless it can no longer measure the depth of bars. Then I turn it into long. The small standard has a smaller electromagnetic field, which makes it easier to get a situation like this. Now, one of the other regions we draw up our reinforcing layout is every reinforced structure is going to have places where reinforcing bars are lapped, or there's additional reinforcing steel from things like seismic or other reinforcing details near columns and walls. So you need to pick and take a bit of time choosing your survey places to isolate individual bars and avoid lapped reinforcing. And I've already highlighted, we want to avoid parallel bars. They will reduce the apparent cover, whether the signal is, whether the bar is above or below the bars being measured. Also, we just need to consider, have we entered our bar diameters correctly? Have we accounted for the spacing between the bars? And just to watch out where bars are on an angle. Something you can always do with the cover meter is push it upwards. We've got indication arrows on the Profimeter that shows if the bar is directly underneath or to the left or right. If you push it upwards and the bar walks left or right, you know it's at an angle to the way you're rolling the cart. When it gets more complicated, well, this is the situation where we discussed that maybe radar would be a useful friend or an alternative. If the cover depth isn't for durability, it's more for just understanding how things are built, maybe the cover depth on a radar is accurate and will make the job more correct. But there are places we can place our cover meter here that are good places to survey. We can isolate single bars, we can find clearer regions. We could even maybe, if we don't have drawings, bring our radar in to find the good spots, take a more accurate, better cover depth measurement with our cover meter and calibrate the depths on our radar from that more precise cover depth measurement. So a lot of functionality. And a lot to consider. The more complex your structure, the more you need to allow for a careful process, destructive confirmation, and use of supporting tools to get the best cover depth measurement that you can. So let's quickly look at a bit of actual examples from the Profimeter. First one, the locate mode. This is just showing how the cover meter can find individual reinforcing steel and isolate it and take the depth measurement. So I move my scanner over, it lines up, and I'm reading a cover depth of 31. And when I get to these more closely spaced bars, they're reading in at 30 as I cross them. I would ideally add, and I can do this on the handheld probe, my neighboring rebar spacing. That'll probably bring it back to a 30 mil, not a 31 mil. Bring it back up to that 31 mil measurement because all these bars are at the same depth. If I need statistics, I know that one of our attendees mentioned they want to take a large statistical data set. I can use spot data. So in this example, I'm going to bring my probe over each bar and I'm going to take a spot measurement, counting up number 1, number 2. This video will speed up in a second and I'll fly past. I didn't add the Benny Hill theme, I'm sorry. But this will let me collect a large data set just of individual measurements each time I locate and just tell it to take a spot measurement. And the outcome of that is going to be that statistical data set. It'll show us our minimum cover, our maximum cover, and all our results. So just give me a second. There's the app popping up. And we take, and it's just a Bluetooth connection. It pulls the file recorded on the probe into the cover meter app. And there's each of our measurements. I can use an indicator to say, is it compliant or not? That gives me, that just helps me clear up. So I'll just show that in a little more detail. So we can see there, I can use indicators. I've got a 12 measurements. Lowest is 29, highest was 31, standard deviation is 29.9. It lets me pull that together quickly. And that's data logging that's available just with the probe outside the hand cut. This is also the functionality that the PM8000 basic cover meter comes with. You do receive the cart, but the basic app doesn't use the cart. You could upgrade if you'd like to use this functionality, but the handheld probe mode is all available there. And if you're comparing to previous models, this is the same as the Profoscope Plus cover meter. Now I'll do a line scan measurement. So again, I'm going to make things more difficult for myself in a second, but for now I'll leave my exposed bars and we'll do a quick line scan over top of those. And we see how we can map out bar position in a straight line. Hold on 1 second. There we are. So letting that continue. So when we do, now we also can show our signal strength, and I am an absolute fanatic for the signal strength view on a cover meter. We talked about how we want to isolate bars from neighboring bars. We can almost see what's happening on this. I can look here and I can see I've got a single bar, that first bar across there, the three I've crossed there, and how the signal from them doesn't die out from the first one till I've reached the second one. It's incredibly informative for the sort of work I tend to, the way I like to teach using a cover meter. I can also move through the same statistical information is available for these line scan views. So let's make things a bit more difficult for the next example. Now I'll just work on the office wall, conventional reinforcing single layer. Now, I mentioned the balance, so I'm going to slide my cover meter down and I'm going to watch that circle on the right here. And I'm going to wait until it shows green and I'm in between the top and bottom parallel bars and then roll across. And now my cover meter is going to, again, find each bar, give my depth. I can give me the same information I had before, but done without line of sight to where the bars are. And you can see that balance coil changing in as I move my cover meter probe back down to the ground. And there's the individual results and the signal that we received. And just again, that statistical information, so number of measurements, standard deviation, and everything else about the spacing as well. So we know we also get spacing information when we're using the line scan surveys. Now the showstopper, let's actually overlay the cover layout here. And I confess I rather damaged the office wall with that tape. It didn't come off very cleanly. But first, I'm going to find my clean survey point. I'm finding the spot in between two reinforcing bars using my signal strength view before I set up how I'm going to do my horizontal scans. We'll quickly mark up a spacing of 200. From my previous measurement, I know my bar pitch is 200 millimeters, and I want my measurements to be every 200 millimeters. So every scan is in between the previous bars. No, Bradley, this particular functionality here, the line scan views, is a pro functionality. We might chat in a second when the demos are finished. So again, I'll get my balance point in the other direction. I'd already checked this, so it's really in line with the side of that tape, but just reconfirming, and then I'll do my vertical scans too. Again, bar pitch here is 200, so everything is now set up to essentially move my cover meter probe through the parallel positions. And I'm going to input that into the app. The plus icon lets me tell it 20 centimeters, 20 centimeters. This is the space between measurement lines. Fantastic. I'm good to go. I'll do the scans essentially like the line scan. We place at the beginning, press the button on the side of the cover meter and take our measurement. And it'll just place, so I'm going to pull it back, get it straight over my beginning point. The line along those arrows is where the measurement occupies. There's the first measurement. The unit, you need to be careful to be in the right starting point, and there'll always be just a slight difference between the bar positions, but they'll line up pretty cleanly, provided we're careful to get our start point. The other thing is when I present this in augmented reality, I'm going to turn on the area scan, which is cover depth for that region. So I've taken my measurement. I've got a reinforcing layout. I'm going to put a target for the augmented reality onto the wall. And now we'll be able to project that measurement using the iPad. So there it is. And that's our projection of the scan in position. Okay. That's sort of the bulk of what I presented today. Did anyone have any final questions or anything they'd like to see demonstrated inside the application before we finish up the main session today?
The signal strength you were showing,
Yes.
that's in the basic functionality, isn't it?
You do have a single strength indicator in the basic functionality. It's just a numerical readout on the scan car.
So I'm looking at starting a project which is going to be a precast project with a lot of what you sort of mentioned before. They're culverts, but they've got some shear cages in them. With that being an extremely busy environment and us needing the quality control check on the depth of the reinforcement, how accurate are we going to be able to get this if we tell it, in the lead-in, to put on the mode? I can't remember what you named the mode, but allow for the bar locations. How accurate are we going to be able to get our readings?
Okay, so there's two ways to think about it: is accuracy of measurement and usefulness for quality assurance. If you can choose a useful value of bar diameter and neighboring bar correction, basically working off a mock-up of your reinforcing cage, you can have it report the correct number over that range. That's what the neighboring reinforcing correction is for, to allow you to work with a slightly denser reinforcing layout to get the depth. Where it gets more difficult is uneven or congested reinforcing. So that's why I call out things like anti-burst cages, where you can have an entire separate reinforcing cage sort of coexisting with a more predictable layout. And in that case, it may be more appropriate to work out a setting and a position on the element to measure, and using that as a go or no go. Sorry, I think I cut you off a little bit there. Was there some clarification?
No. You sort of you've answered the question there. Functionally, it'd just be a combination of some destructive testing to prove what we're reading in that area that we can then read with non-destructive testing.
Absolutely right. And that's actually when you start doing forensic level surveys with cover meters, there is usually that destructive confirmation too, that confirmation of are all the settings we've chosen giving a value that's right, or do we need to make an adjustment to get the very best setup to measure accurately over the rest of the area? There's nothing like a destructive test to make you feel confident.
How well? So the thought is to combine the two of them and, first unit of each type, do some combination destructive testing so that we can set the parameters for that unit type. The question would be then, once we've got the parameters for that's the cover, how accurate is it to create the image of the map, the reinforcement inside the unit, so we can check bar locations after the fact? Okay. I know it looks bloody fantastic for creating it when you're looking for a sheet of mesh, but if we've got that congested reinforcement environment, how good is it going to be at locating the congested reinforcement? Okay, really good question. Really important question. So this is I'm doing this live on my app. This is the most powerful tool to work out if what you asked for is going to work. So this is the cover meter signal. So this is not cover depth. This is the raw signal received by the cover meter. And what happens with the actual measurement procedure is at every peak in this chart, it places a bar. So when we have a slightly uneven reinforcing layout like you're talking about, if you were to take your cover meter over that and see a distinct pattern of humps and dips, you will be comfortably able to do all of the visualization tools, because the visualization tools rely upon the placement of bars at the peaks of signals. Now, something that can happen on those signal strengths
is you can get a very flat signal strength. Now, that flat signal strength will not correctly place bars because it can't find a peak. But if your neighboring rebar correction and your choice of bar diameter are correct, your depth measurement will still be useful. You'll still be able to do spot checks of depth in those regions, but you may not be able to produce visualizations of bar position. That's the specific contrast. If it's an important output from the machine, do get in touch after the webinar. We can set up a trial to see whether the visualization functions, as opposed to just say the basic spot measurement modes, are going to add to the project.
Thank you.
Is does that answer the whole details?
That answers the questions that I've had, yes.
Great. Cool. So any more questions before we turn off the recorded section of the webinar?
No, it has been very useful, William. Thank you very much.
No problem. I'm glad to get to go through this.